So 3.1b is all about derivative graphs. So we'll start by drawing a picture. So my notes are graph paper to make it a little easier for me to make a graph that looks good, but we'll see. Of course, I start out bad. I didn't actually make it big enough. So I'm going to do maybe that big. Go across. So let's graph the function y equals x squared. So if we do that, we have the point 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. And then we can connect it, and that's, not bad. Not great, but not bad. So now let's talk about the derivative. So if we take the derivative with respect to x, d dx of x squared, we will do the limit as h approaches 0 of f of x plus h minus f of x over h, which is the limit as h approaches 0. F of x plus h is just x plus h squared, and f of x is just x squared all over h. Limit as h approaches 0, x plus h squared is x squared plus 2xh plus h squared, and then we have minus x squared over h. So if you can't tell by looking or kind of memorizing x plus h times x plus h what that equals, just go ahead and do it on the side. That's totally fine. So now our x squareds cancel, so we end up with the limit as h approaches 0 of 2xh over h, which is 2x, plus h squared over h, which is h. So as h goes to 0, we get 2x. So the derivative of x squared is 2x, which means the function that denotes all the slopes of all the tangent lines for y equals x squared is going to be 2x. Well, let's find some points. So f prime of negative 2 is just 2 times negative 2, which is negative 4. F prime of 0 will be 2 times 0, which is 0. F prime of 2 will be 2 times negative 2, or I'm sorry, 2 times 2, which is 4. You could do the ones in the middle too, but I'm just going to do those three. So then our points that we have are negative 2, negative 4, 0, 0, and 2, 4. And if we connect those with a sort of straight line, it's not really that straight, there's our derivative. So this is y, and this is y prime. And guess what that line is? 2x. Okay, so that's the equation for our derivative. So for derivative graphs, so let's show a couple things here. That's a terrible line. And I even have lines and I'm not even following them. Okay. There we go. There we go. Okay. Let's say we have this line. It's the line x plus 1. Okay? If we try to find, sorry about that. If you try to find the slope here, we'll have, sorry guys. It's the stay put drill, as you probably have gathered. Okay, so we have the line y equals x plus 1. And then if we try to find our slope, or the slope of the tangent line all along here, well, if we look, the slope is just up 1 over 1, 1 over 1, up 1 over 1, up 1 over 1. The slope is 1 all the time. So our derivative graph is just the line y equals 1. So y prime equals 1. Y equals x plus 1, y prime equals 1. So that's what we do when it is the graph of a line. Sometimes our function is just a horizontal line, like the line y equals 2. Well, if you look all the way across and find slopes here, the slope is 0, 0. The slope is just 0. So the graph of our derivative would just be y prime equals 0. So as far as finding the graphs of derivatives, they get a little complicated sometimes. So I wrote out some steps for us to use. So the step 1 is locate x-intercepts by finding where the tangent line is horizontal. Basically looking where the slope, or m, is 0. Then we draw vertical lines at our x-intercepts. Then we draw vertical lines at cusps and corners. So cusps, when the graph does like that, and corners are more like that. But essentially, if it comes to like a point anywhere, you can't take the derivative there. It's a cusp or a corner. Step 4, for curves, shade above or below the x-axis, depending on what your slope is. Step 5, for lines, the slope will be constant, like we looked at above, a horizontal line. Cusps and corners and holes will all be holes in the derivative graph. Because cusp and corners, you can't tell what the slope is. Basically, the slopes are different on either side. You can't tell where you draw the tangent line. Holes, if the function doesn't exist, you can't have a derivative. Sorry, in the derivative graph. So you pick up your pencil after you draw a hole, and you start in the next region with another hole. I'm going to show you a couple derivative graphs. Actually, I'll show you more, but right here I'm going to show you a couple. So let's say we have a parabola. So our first step, if we look up at our steps, is to locate x-intercepts by finding where the tangent line's horizontal. The tangent line's horizontal right there. That's the only spot, because otherwise if you drew tangent lines, they'd look something like that. Well, better version, but the horizontal tangent line is there. Basically at a minimum is kind of what happens. So there's our x-intercept, about, if I was better at drawing. And so then our next step was to draw vertical lines at x-intercepts. Then we draw vertical lines at cusps and corners. I don't see any. For curves, we shade above or below the x-axis depending on the slope. So on the left side of this x-intercept, since this is going down, it has a negative slope if you were to draw the tangent lines. So I'm going to shade under here. On the right side of the x-intercept, the function's going up. So that's positive derivatives, positive tangent slopes, so I'll shade up here. So when graphing this derivative or tangent, or the slopes of all the tangent lines, if this is f, to get f prime, going left to right, we kind of draw in the blue. So we start down here somewhere, cross through the x-intercept, and go up to the other blue, f prime. Does it look exactly like that? I don't know. It's pretty close. That's all we're going for. For another one, let's say our graph looks like that. Our first step was to find where the tangent line is horizontal. That'll be right there. We go down here. There's our x-intercept. We do a vertical dotted line. Then we draw vertical lines at cusps or corners. Here's a cusp. I'll draw a vertical line right there. For lines, slope will be constant. So really now we can just go left to right, okay? So for lines, the slope will be constant. Actually, you know what? We should shade first. So to the left of this cusp, it's going down, so our slope is going to be negative. In between these two, this isn't really an x-intercept, in between the cusp and the x-intercept, the function's going upwards, so we have a positive slope. And after that x-intercept, going downwards, so we have a negative slope. So to graph our derivative starting at the left, well, over here, we're just going to have a line, because that's a line up there, so we have a constant slope, horizontal line, and then we hit a cusp. I'm going to make a hole. Okay, well, now I have a hole. When you have a hole, you pick up your pencil, and then you start in the next region, which is up here in the positive somewhere. I don't know exactly where. Let's say here. And so from here, we'll have a positive slope, but I know I need to go through this x-intercept, so it's going to be positive, and then it'll be down to this blue part. Something like that.